Okay, in this video I'm going to continue on with my tutorial series on thermodynamics and statistical mechanics. This is tutorial number 7 and we're going to discuss enthalpy. Enthalpy is a fundamental concept in thermodynamics, in particular for chemistry. So the previous video to this was where I discussed heat capacities, and that's where I'm going to start, because if you thoroughly understand heat capacities, then you can thoroughly understand enthalpy. And I'm telling you that if you don't understand what I'm about to explain in terms of heat capacities, you will struggle when it comes to understanding things like the Gibbs free energy or the Helmholtz free energy. So where am I going to start today? I'm going to start today by trying to understand why the heat capacity at constant pressure is greater than heat capacity at constant volume by an amount, the molar gas constant, for 1 mole of gas. So where do we start? Well, we start with the definition of the heat capacity. Now, perhaps I should have discussed this in my video on heat capacities. I actually did, if you think about it. Well, as you'll see in a moment, I actually did, but I didn't go into much detail because it wasn't necessary then. So we know that the heat capacity, capital C, is equal to Q over the change in temperature, or is equal to the change in internal energy minus the work done, like that. And then what we did is we said that there are 2 cases to examine. One when the work is equal to 0, and 2 when the work was not equal to 0. So I'm going to assume for the moment that there is no other sorts of work being done. There is no electrical work, there is no whatever. There's no electrical work, for example. There is, like a battery, for example, has electrical work. So the only work we're going to have in this case is compression work, compression or expansion work. So the work can either be 0 or it can be greater than 0. Now, the only way this can be equal to 0 is as follows. We know that the compression work, as seen in a previous video, is the integral minus the integral of P dV. So the only way for compression work to be 0 is if there is no change in volume or we have an isochoric process. And this is important. The whole idea of an isochoric process is very important. Now, look at the first law, delta U is equal to Q plus W. The only way you can increase the internal energy of something is by, if we're only talking about compression work, is either by adding heat or by compressing my system. But I'm just saying that the system, I'm going to say, is a constant volume. So therefore there is no compression work being done. Now, anytime I say constant volume, I'd like that you actually sit back and think of a closed box. Think of a closed system. Think of a closed box. So if the volume of this box isn't to change, the only way I can add energy to it is by heating it. I've reduced the number of ways I can add energy to my system by quite a large amount if I can't compress it. Alright? So, when we said that when the work was equal to 0, so when work compression is equal to 0, it's delta V is equal to 0, and we get that the heat capacity is a constant volume, and we got delta Q over delta T, or delta U, excuse me, over delta T at a constant volume. Alright, so now we know we have a certain, that's a certain number. But if the compression work is non-zero, is not equal to 0, or in other words, it's greater than 0, say we're compressing it because we're looking to add energy, then delta V is non-zero. So that means we talk about a constant pressure process, generally because it's easier to do things at constant pressure, or we can do things either at constant pressure or at constant volume. And we had some sort of an expression for it, which I'm not going to go into, but we showed that the expression could be written this way for 1 mole of gas. So I'm hoping that you see the reason that a constant pressure process requires more heat in order to raise the temperature. It's because we are actually doing work against the surroundings. So if it's expanding, your system is doing work against the surroundings, which is increasing the amount of heat you need to put in. Whereas at a constant volume process, there is no compression or expansion work, and as a result, the amount of heat required is less. So constant volume means there's no compression work. Constant pressure, however, means there is compression work, which increases your heat capacity. So let's continue on from there. I hope that's clear, because I will be discussing it again when we talk about Gibbs and Helmholtz free energies. So, to start, constant pressure processes are common, in particular in chemistry. Constant pressure. So, in a constant pressure process, we prefer not to look at energy changes because they're difficult to calculate. Instead, what we look at is we look at making room for a system. Making room, that's what we look at. So, what does making room mean? Well, making room is expanding against the surroundings. So, at this stage, you've seen quite a few times that work done is equal to minus P delta V. Now, if we're making room for something, well then delta V is positive, therefore we get negative work. Like that. So your system is doing work against the surroundings. Right? We've seen that quite a few times. So, if you think about it, if I want to make a system out of nothing, what do I have to give it? Well, as I said a moment ago, I need to make room for it. So I need to make P delta V. So to do negative work, my system must do negative work against the surroundings. And also to make my system, I need to add some energy, internal energy. And I call both of those together the enthalpy, capital H. Enthalpy. It should make sense. To make a system at constant pressure, I'm able to do compression work, or expansion work actually in this case. So here's my doing work against the surroundings at constant pressure, and here's the internal energy of my system, and we call that enthalpy. So how do I get the change in enthalpy? Well, the change in enthalpy is going to be as follows. It's going to be U plus delta U plus P outside of V plus delta V. That's going to be equal to delta H. Let's say H plus delta, that's H plus delta H. Alright? So you can rearrange this as U plus PV plus delta U plus P delta V, or delta H plus H. So we see this is H, so cross it out here, and we see that delta H, the change in enthalpy, is delta U plus P delta V, as we would expect. Okay, so I'm going to move on from there. So let's rewrite our formula. We have that delta H is equal to delta U plus P delta V. So if we look at this formula, how do we change the enthalpy of our system? Well, we either change the internal energy, which is usually done by heat, or we do some expansion work. That's to increase the energy, or the enthalpy. Obviously, if you can do some compression work if you want to reduce the enthalpy. So let's look at this then. We know that the first law says that delta U is equal to Q plus W. Now remember, the work done is Q minus P delta V. Because the work done is positive when it is being compressed, and it is negative when it is being expanded. So if delta V is negative, it's being compressed, and this will become a positive number here. Okay? So the change in energy, the change in internal energy is Q minus P delta V. So let's plug that in. What we get now is that delta H, the change in enthalpy, is equal to Q minus P delta V plus P delta V, which is already there, which these go, leaving Q. Alright, now of course, I said there are lots of different ways of doing work, but this would leave other sorts of work, like electrical work. We can put that back in right now, no problem. So that means that the change in enthalpy is equal to the heat input plus any other work besides compression or expansion work. So that means the enthalpy is not changed by compression or expansion, but only by heat and other work. Okay? So, if the other work is equal to 0, as we said, we have delta H is equal to Q, which makes perfect sense. Now, the last thing I'm going to talk about is an interesting property. What if I take, actually, just let me clear up my board. let's go and look once more at the enthalpy. H is equal to U plus PV. What if I take if I get the derivative with respect to T? So del T at constant pressure of H. Well, that's going to be equal to del T of U plus PV at constant pressure. Let's say I put the P here. Alright? Now, the internal energy, we know that, because we've seen it, we'll say del H, del T, constant pressure. Let's assume that our system obeys the equipartition theorem. Therefore, there is a half kT kinetic energy per degree of freedom, and as a result we get del T, constant pressure, of half N, the number of molecules, F, the number of degrees of freedom, K times T. Okay, and we can rearrange this. We'll say we can put in the ideal gas law here, as I did in the previous video. I rearrange this to NKT. PV is equal to NKT. We know that. So let's just do the derivative. So del H, del T, at constant pressure is equal to 1/2 the number of molecules times the number of degrees of freedom times Boltzmann constant plus NK. But that's exactly how we defined the specific heat capacity, or the heat capacity, excuse me, at constant pressure. So del H del T at constant pressure is equal to C sub V plus R is equal to the heat capacity at constant pressure. So a way of measuring the heat capacity at constant pressure is to look at the change of enthalpy with respect to temperature, or vice versa. Okay, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood you might also click on an ad. Thank you.